Okay, guys, we're going to be covering pages 3 through 5 in the new triangle trigonometry packet that you guys have. And we're just kind of reviewing some of the right triangle solving techniques that we've known before. So you'll see some Pythagorean theorem and SOHCAHTOA using those to help us find sides and angles for these triangles. I will move kind of quick through this video, so please make sure that you pause whenever needed and make sure that you practice with the other problems on these pages. We're going to use these techniques when we start learning about vectors in our next video. Okay, without further delay, let's look at problem 1. So problem 1 says a surveyor is standing 115 feet from the base of the Washington Monument, and he measures the angle of elevation to the top of the monument as 78.3 degrees. Now we want to figure out how tall the monument is. So why don't you take a second, try to draw that triangle and make a diagram for us here. And if you draw the triangle out, you should get something that looks approximately like the diagram I drew in green, right? You have 115 feet at the bottom as the distance that the surveyor, I'll draw a little stick figure so you can see him, is standing away, and he looks up with this angle of elevation. Remember, angle of elevation is always rising from the flat horizontal, whereas angle of depression is always going downwards from the flat horizontal. We want to find the height, which I've marked over here on this side as x. So what we can do, based on this angle, I know the opposite and the adjacent side. You should be able to figure out by this point, hey, that means I know a tangent equation or a setup for tangent, and I should get this. Tangent of 78.3 degrees equals x over 115. And if I multiply both sides of this by 115, I'm going to be able to get that x by itself pretty easily. Once I've done this, I should be able to get that x equals 115 tangent 78.3 degrees, which is approximately 555.314 feet. And I just rounded off to 3 decimal points. But that would be the approximate height of the Washington Monument according to this problem. Okay, so guys, this should all be review. Throwback to what we did when we talked about right triangles. Now, we could have also used something like law of sines or law of cosines to help us here if we really wanted to, but with right triangles, we don't even have to go that far. We can just rely on the old SOHCAHTOA tricks. Okay, next up is problem 2. Now, problem 2 is a little bit convoluted in terms of wording, so let's make sure that we've got this down. A historic lighthouse is 200 yards from a bike path along the edge of a lake. A walkway to the lighthouse is 400 yards long. Find the acute angle between the bike path and the walkway. So from what I understood here, we've got a lighthouse at this blue point right here. I'm going to call that my lighthouse. And 200 meters away from that, or sorry, 200 yards, is this bike path. Okay, and I want to find an angle from this bike path. There's a walkway that connects back to the lighthouse. That is 400. Okay, so if you're not sure, over here, this 400 is the walkway. And this 200 yards is the distance to the bike path. So this is the path. And I want to figure out what this angle is. Okay, so in reference to this angle, let's label our sides. So across from it, this 200 yards is my opposite. And of course, this 400 is going to be my hypotenuse. So which ratio, those old SOHCAHTOA, that uses those two numbers? Hopefully you should have come up with sine. Go ahead and take a second. You guys try to solve this before you look at my solution. So you should have gotten the setup that sine theta is equal to 200 over 400, the opposite over the hypotenuse. And in order to solve this, we could go about it two ways. One way is we can reduce this down to being 1/2 and say, hey, sine theta is 1/2. We could look that up on the unit circle, or if we were relying on our calculator because the number wasn't so friendly, we could do the sine inverse of 1/2. And we should find that this is actually 30 degrees. Okay, so again, we're back at solving for those angles. Just like when we use law of sines and law of cosines, we have to make sure that we use this inverse anytime that we're looking for an angle, and that will get us to our final answer, 30 degrees. Okay, guys, if you flip the page and you look at page 4, question number 4 is talking about solving the triangle below, which means we need to find 3 quantities. We're looking for all the information that they haven't told us. Now, one piece of information that they did not mark on the page, but we do know, is that C is actually our right angle here. So now we're going to want to solve for small a, small c, and big B. All right. And think about back to our law of sines and law of cosines. How can we solve this? What's a good starting point for us? Hopefully you came up with that angle B is probably the easiest thing to solve for because we know the angles add up to 180, so we can do 180 minus 34 minus 90, and that should leave us with 56 degrees, which is big B. So here we go, that is 56 degrees. All right, and from here, now that I've gotten that angle, we have all the angles. We can just use our sine, cosine, tangent setups to help us solve these. I'm just going to go ahead and show you the setup for tangent to solve for A, though there are multiple ways to get to this answer. Okay, so I said, hey, the tangent of 34 degrees is equal to A over 19.4. Okay, and what we'll do after that is we'll multiply that 19.4 to both sides, and we'll use that to solve for that little a up at the top. So now that we've gotten that a is 13.085, we can actually solve for c. We have a couple options. We could use Pythagorean theorem. We could also set up a cosine or another version of that to solve for this. Okay, so I'm just going to show you with the cosine setup. So I said, hey, following from the same angle, I've just been referring to angle A, cosine 34 equals 19.4 over C. And if I get C by itself, I should solve and find that this is 23.401. Okay, so that's based on this setup right here, getting me to 23.401. So hopefully you can solve this triangle and find all the missing pieces, including that last angle that we started with. Okay, it's very important that we remember this rule that all the angles add up to 180, and remember how we set up sine, cosine, and tangent to solve for individual pieces. Don't forget Pythagorean theorem is still a part of right triangles. We can still use that whenever we want. Okay, now on to something new. Okay, we're going to talk about bearings. Now, bearings is kind of an interesting topic because it deals with navigation, and there are 2 different forms that we'll talk about. Now, the very first form of bearings always starts from the north or south line. Now, the easiest way to think about this, if you look at a piece of paper, north is always going upwards, okay? So remember that. This is important detail. North always faces the top of the page, okay? And from there, you can determine east, west, and south, obviously going around clockwise. Now, how do we write a bearing from this? Okay. All we do is we always start at north or south, and we see what angle am I swinging out. Okay. So, for example, in this very first one, you can see in the first picture that, hey, you would start at south and you swing 35 degrees to the east. So what are you going to say? You're going to say, hey, I start from the south, I go 35 degrees, and I am going in the east direction. And this reads as 35 degrees east of south. Okay? You always start from a cardinal north or south, and you go east or west from there. Okay? So the second example that they show you is starting from north goes 80 degrees, and you're like, oh yeah, that started from north, I went west, so north 80 degrees west, which reads as 80 degrees west of north. Okay. Now, the last one is kind of interesting. It is 45 degrees, and the one cool thing about this is true northeast, and all that means is that's actually the northeast on your compass. So if you ever hear a problem say or someone say, hey, it's exactly northeast, that means it's 45 degrees between north and east. All right. So again, guys, start from north south, then go either east or west. That angle that you go, that's going to be the angle that you put in the middle. Okay. You're always going to have north or south first, and then you'll put your east or west last. Awesome. Let's put some of that bearings knowledge now into action. So our first example says a ship leaves port at noon and heads due west 20 knots or 20 nautical miles per hour. And at 2 p.m., the ship changes direction 54 degrees west of north. Now we want to find the ship's bearing and distance from the port at 3 p.m., so after 3 hours. All right. So I'm going to start tracing out a diagram for this first, and then we'll try to put the whole thing together. All right. So again, remember, guys, north is going to be facing this way. All right. Always to the top of the screen, top of the page. That's where we're going to be facing north. All right. And I start by going 20 knots or 20 miles per hour, and I left at noon and I get to this point at 2. So I realize here's where my ship is starting, and I'm going due west, so flat west, for 2 hours. And that's going to give me 20 times 2, which is 40 miles, is the length of this piece right here. Now, having gotten that piece, I now change directions and I'm going 54 degrees west of north. So I'm going to kind of trace this just so that I can understand it in my mind. Here's my north line right here. Okay, so that is north. And I'm 54 degrees west of that. So here's a 54-degree angle. And my ship is now continuing to travel along this path. And it travels 20 miles because it's only 1 hour this time along that. What do I want to figure out? I want to figure out, starting from the port, I need to figure out the distance from this point to this point. So first question, what is this distance? And the second question is, can we come up with a bearing for this? All right. And to get the bearing, the first thing we're going to need to also solve for is going to be this angle right here. All right. So we're going to want to figure out two things. I need to figure out that angle theta and that length x. Now let's think about how could we do this? This is not a right triangle. You can tell from the diagram something's off here, not at a right triangle. So we're going to have to go back to law of sines and law of cosines to help us with this. So one thing that we're going to need to figure out in order to solve for x is how big is this corner angle? And one thing we should note is that there is a right angle actually hidden in this triangle right here. So that angle that's marked in white is actually 90 degrees plus 54 degrees, giving me 144 degrees as this angle right here. Okay, and that angle is going to help me solve for x. So I'm going to set up law of cosines to solve this. And if we want to keep it simple, let's just label our triangle ABC. So I'm going to go ahead and just start by putting A in this bottom corner. So here's A, here's B, and here's C. And you could label it with different letters if you wanted. C, here is little a, and here's little b. So we're going to try to solve for big A and little c. Those are going to be kind of the key points of information that we need. All right. And I'm going to start by setting up law of cosines to solve for little c. Go ahead and you guys do the same thing and then check your work against mine. So you can see I went ahead and set up law of cosines right here. And I'm going to get c by taking the square root of whatever number I get. And I should get c is equal to 57.397 miles. And that's actually the distance from my port to where the ship currently is. Now, once we've got this, we'll now be able to set up and solve for the missing angle here. So let's go ahead and just use law of sines. I'm going to scoot this up a little bit. And we'll use law of sines to solve this. Go ahead and try to set it up. Remember, we're looking for big A. Hopefully, if you started setting this up, you're going to have 20 over sine big A equals, and let's use C, 57.397 over sine 144. We'll go ahead and cross multiply, not forgetting to take my inverse, and I should get that big A equals 11.819 degrees. That is my second quantity that I was looking for. Now that I have this, let's go ahead and try to answer the actual question, which said, hey, what is my bearing? All right. So to figure out the bearing, let's go back and look at our question for a moment. We already know that this angle is 11.819 degrees. And we have the distance already for C. Now, remember, your bearing has to start from where? Either north or south. And in this case, since my angle is pointing upwards, I'm going to go ahead and say that it should start from north. So if we look at this, here is where north is. My bearing is going to be this angle right here. How do I figure out that purple angle? What should I do? Hopefully you came to the conclusion that, hey, that angle overall is a quadrant and it's 90 degrees. So if I did 90 degrees minus 11.819, I can calculate the bearing for this. And my bearing is going to be starting from north and going west because that's the direction you can see that my arrow is facing. So we're going from starting from north, and I'm going, this is going to give me 78.181 degrees to the west. Okay, so this is my bearing right here. Okay, and this is my distance. So those were kind of the two things we were looking for, the bearing and the distance. Now, solving the triangle was part of it, but putting that bearing together is kind of the tricky part. This number came from subtracting it from 90. Sometimes we really do have to look hard at that picture and figure out what angle am I really trying to ask you for. Okay. Remember, these bearings always have to start from north or south, and they're going to go in whichever east-west direction that you want. All right. So that is my distance to the ship, and this is my bearing. Okay, guys, let's do one more example of bearings with a sailboat. So a sailboat leaves a pier and heads due west at 8 knots. Remember, that's 8 miles per hour. And after 15 minutes, the sailboat tacks, changing course north 16 degrees west. And it's now traveling at 10 knots. Find the sailboat's bearing and distance from the pier after 12 minutes. Okay, so the challenging thing is here, guys, figuring out how big each side of the triangle is. All right, so 15 minutes is only 1/4 of an hour, and 12 minutes is 1/5 of an hour. So we're going to use those along with the speed to figure out how large this is. I've got my starting point, the pier. I'm going to go due west. 8 by 1/4 is just going to be 2. I'm going to go a little bit faster when I turn. This is going to be 10 by 1/5, which is also 2. And this angle right here, remember, based on the bearing they gave me, I start from north, add an extra 16 degrees on there, and you should see, hey, my angle right here is going to be 106. That is 16 plus 90 degrees. And I'm going to try and figure out again, long side of the triangle, we're going to want, can we figure out the bearing and can we figure out the distance? So again, let's use law of cosines here. All right. Based on what we know, that seems like the best bet. Let's just call this A, B, and C. let's start solving for little c. Okay, so if we start solving for little c, we can say, hey, again, c squared equals 2 squared plus 2 squared minus 2 cosine 106. And we're going to find that c is 3.195 miles. And that's going to be my distance from A to B, from where the pier is to the sailboat. And the next thing is, let's figure out the angle. So remember, I'm going to need to figure out what angle B is. And we can kind of cheat here because this triangle is isosceles. So we could use law of cosines if we really had to, or law of sines, but we can actually figure out that A and B are both equal, and they should both be equal to 37 degrees. So with this information, let's try to come up with this bearing. So again, where do my bearings have to start from? They have to start from either north or south. Again, I'm going to start from north. So here's my north line. And I'm going to go this way. I want this green angle is my bearing. All right. So that angle is going to be 90 degrees minus the white B, which is 37 degrees. Now, when I subtract this, I should get 53 degrees. And let's set up the bearing. I started out at north and I ended going towards the west. So here's my bearing. And I already found the distance up here as being 3.195 miles. All right. Now this one's pretty tricky because of these distances being a little tricky to figure out because of the time. But as you can see, once you have the angles of the triangle, you just have to set up a bearing based on either north or south, 90 degrees, right? And you're going to subtract to get that individual bearing for this. Okay, let's talk about the second type of bearings, which is dealing with air navigation specifically. Okay, so anytime we really talk about planes, maybe hot air balloons or something like that, anything that flies, we're going to use this type of bearing. Okay, and our note says, hey, this measures degrees clockwise from north. So we don't even have to say, hey, am I starting north or south? No, we always start north. And interestingly enough, we go clockwise instead of what we're used to. Okay, so let's look at this example and see if we can come up with our bearing for this. I have an airplane that's flying 125 miles north and then 75 miles east of an airport. What bearing should the pilot take to fly directly to the airport? Okay, let's figure this out. So I'm going to say, here's my airport in red. My plane has gone 125 miles north. Okay, again, remember, guys, north is always at the top of the page. And 75 miles east. Okay, so there's my 125 and 75. The pilot wants to be able to turn back and make it to the airport again. And I just really want to figure out what that bearing is. Okay, so if my plane is over here at the white marker, we know that I'm going to need this angle somehow. And good news, guys, this is 90 degrees right here. So we can definitely solve this using the old SOHCAHTOA. We don't even have to go all the way to law of cosines. So knowing this information, 90 degrees right here, I want to figure out this angle. What can we say about the sides that we know? Well, this 125 is across from my angle. So I'm going to call that my opposite side, and 75 is my adjacent. Hey, which ratio used the opposite and the adjacent? Hopefully you guys came up with that we could use tangent theta to help us solve this. And you should get that, hey, remember opposite over adjacent, so 125 over 75. And to get just the angle, I'm going to have to use that inverse again. So theta is tangent inverse of 125/75. So if I plug that in my calculator, I'm going to get that this is 59.036 degrees. And that's this theta angle right here. Now, remember, air bearings are measured from north. So let's make a mark at north. Here's north. And I'm going to go around clockwise. So I'm going to say, hey, I need to go all the way around to here. And I need to figure out how big that angle is. Now, this can be a little bit tricky. How am I going to figure out how big that angle is? There's a couple of different ways we can look at this. Number one, the whole circle has to be 360 degrees. So if I take away the other portions from 360 degrees, I can figure out how big that angle is. This section that we haven't talked about is 90 degrees. I know this section is 59.036, and we can solve it like that to figure out how big that angle is. There are a couple other ways we could work our way to the same conclusion, but this seems like a good enough one for us right now. 360 minus 59.036 minus that last 90 degrees to give us this yellow portion right here. And we should get that that is 210.964 degrees. And that is my bearing for the plane, okay? Air bearings, guys, don't have any kind of indicator like north or south or west or east. They always start from north and go around clockwise. So if I told you, hey, 210 degrees should be your bearing, you know to face north, turn 210 degrees, and you'll be facing the correct bearing. All right. So guys, that's the two kinds of bearings in a nutshell. All right. One of them starts from either north or south, and the other one always starts from north. Okay. So make sure that you keep this in mind when you're solving problems and you get asked for a bearing. Make sure that you think, wait, am I in the air or am I on the ground or sea? Right. Sea and ground will use that first style of bearing where we pick north, go however many degrees, and then put your east or west, versus flying a plane, you're going to use this style of bearing, okay? As we continue with this topic, we're going to find easier ways to actually calculate these angles, so we won't be jumping through as many hoops of, setting up law of cosines and law of sines to figure stuff out. We'll start using some different techniques that will help you make this process simplify. But the important things to take away from this video are, how did we find these bearings, and which type of bearing do we use for each problem?